Of computational intelligence, as you can see, of Otto Goethe University in Magdeburg. She is also a very active member of the World Organization of IEEE Computer Intelligence Society, also promoting having more women in our specialty, which is very nice. So since everything else was already said yesterday, and you probably want to hear her and not me, please.
Thank you. Good morning, everyone. Okay, so I continue what I was talking yesterday about. It's on multicriteria decision making. Making decisions is always difficult, at least to me. And for this talk, I have a long outline, but I cluster them into certain parts, so it will be not so long. So what I will talk about first is like, okay, multicriteria decision making, what approaches are there? Then I focus on human users, how can we support humans to make decisions? And then I immediately afterwards, I go towards machines. Talk about one machine, how can a robot or a bot or an agent learn to make decisions? Well, how can it make decisions, and then how can it learn to make decisions? And then I increase the number of agents to a swarm of them. We call them collective. And then I say, how can a collective make a better decision? And then how can we influence the decision making of a collective? Like the election in the United States, how can you influence people making decisions? But that is for machines, so I'm not touching that topic of election, because this is on its own a topic of, well, it will take a long time. Then I will talk about how you can have a swarm of robots or agents learn to solve multi-objective tasks, and I think you know what is a multi-objective problem by now. Then I talk about how you can understand decision-making in human brain, the little project. Maybe you can be inspired by that and apply that on your own approaches. Then I show you some videos of real hardware, the robots in my lab. Jim, you have seen some of them. They can now make decisions, or at least we believe that. And then at the end, when you talk about decision making, you have also to talk about ethics. If you have a machine that is making decisions. I'm not an expert in that area, but at least I want to bring one idea there that, you know, this is really getting close to the ethical issues in there. So multi-criteria decision making, you already know. We have several objectives, functions, we want to optimize at the same time. And during this talk, I'm talking mostly about minimization, but sometimes maximization. And the solution of such a problem, as I said yesterday, is a set of optimal alternatives, and you can use existing approaches, like we were talking, evolutionary algorithms, or even weighted sum, or any other approach, to find a set of alternatives. After that, we have to make a decision, to take one. If you are an engineer, you find all the alternatives and say, okay, now I have to do that, and there are lots of decision support systems. You can buy them. Even MATLAB has a decision support system, and then you can take one of them. Making decision is always good if you have many alternatives. It gives confidence to us. So if you still know what you want to buy, for example, if you want to buy a car, you have two criteria, cost and the fuel consumption. Still, if you have a set of alternatives, and still even if you know that you want to buy a Honda, let's say, but if you have the alternatives there, you are more confident about your decision. This is, for example, critical for medical treatment plans. One of the projects that I have, for example, in the cancer therapy, the doctors, they know what is the answer. But once we give them a set of alternatives, he is even more confident that his choice was a good choice. And he can also convince the people, look, these are all the alternatives, but if you want to optimize this and that, in the personalized medicine, this is the best thing that you can take. So decision making is good. Now, you remember yesterday, the example, I will bring another slide, but this is the way you make the vanilla version of making decisions. So you set a weight vector say, okay, the first objective is this amount of weight. We call them R, if you have two objectives. And then you say, okay, the first one has this importance to me, the second one has this one. You have the number of objectives, where that could be M. And then you go through all your set of solutions that you found and select one which fits your choice, your preference. The only problem is that you might not know this weight vector, and you might have too many alternatives. And remember this example, the weight vector might not be a good choice. But let's put that aside and imagine that we use the weights now. Good. So let's imagine this is the, let's say, base of decision making. You set the weight. You can also use actually other approaches. For example, you can use the epsilon constraint or other standardization functions. You can use them to select one of them. But the problem now, what I want to show is the number of solutions. Here is an output of one of my algorithms with 3 objectives. If you give that to a decision maker, he says, what can I do with that? You visualize that. You cannot select anything. You know basically the extreme points if you have 3 objectives. If you have many objectives, you can use parallel coordinates. You put the bunch of optimal solutions that you're very proud of. You could find a set of diverse solutions, give it to him, and he cannot really select anything. And next to that, you do not even show how the decision variables, the x variables are. You show only the function values. You don't show how these solutions really look like. So there are works from colleagues in Japan, for example, they try to visualize using the self-organized maps. They try to visualize the search space. This is the wing of an airplane, and you find a set of optimal solutions, and they cluster them, as you guys are doing with the clustering, and they can show this huge 1,000-dimensional space, or I don't know here how large, but they show it in 2-dimensional space, so you can say, oh, okay, I want to have a wing which looks like this, so you can select any solution in the middle or so. You can also use heat maps. Every row here is one solution, but it is too much. The decision maker cannot select any of them. And the question is, what they ask us usually, give us more information about this. This is not enough. And this community on evolutionary multi-objective optimization is now realizing, okay, we have to do one thing more. So, and also there is something which is called Higgs law. Higgs says that if you give a human being more than 7 alternatives, he cannot make a decision. So, now the question is, can we do something better? Can we find some information? And Jim Keller yesterday said something about the knee points. So, the question is, look at here this Pareto front. Can we find some interesting features here? So imagine we compare, let's say we are minimizing F1 and F2. We are minimizing. And we compare, let's say, A and C. A is a little bit better than C in terms of F2. A little bit. Really not much. But C is much better in terms of F1. So if I give you this set of Pareto optimal solutions, these are all non-dominated, you might not be interested to have A, because A is giving you, and if you have a little bit of mistake in your, or uncertainty in your modeling, that is really not good to get A. So what we are interested in, to find the knee points, the knee, like the knee of the human being. So I don't know how you do that, Jim, but, huh? MATLAB. So what we do is that we write the code for that MATLAB. So how can you identify these points that are the knee points? And for that, you remember the domination criteria I was talking? That was this point, A dominates this area. Why? Because if you compare A with any solution here in the dashed area, and you are minimizing both functions, A is better than the solution here, because it is better than F1 and F2 than the other one here. So now, and yesterday we were talking about epsilon domination, I changed that now to something which is called cone domination. The cone domination is that you dominate a larger area here. And how does it work? So basically you open these two lines, so you transform this function f, f1 and f2 that you use here, this horizontal and vertical line, to two new, well, you transform them, so I can show here. You transform them to new function, omega. And that omega is telling you how you open this, the cone. I think it's too early. I see in some of your faces that is, oh, I don't want to go through the math, but it's basically simple. If I, so instead of f, you compare the omega values, and the omega values look like, for example, you need a matrix here. This matrix, the elements here, they show us, for example, how you open the cone. For example, if you have a matrix like this, you dominate an area which is here. And if you have this matrix, you dominate an area which basically the horizontal line stays the same because you have a 0, and here you are changing it. You can generalize that, and I put this slide for some of you who is interested to look at it later. You can open it using generalize that, open it for a fee, and then you have to decide how much it should be. But if you open it, then you can actually focus on certain parts on the parietal front. Example, the parietal front to objective. If I have this case 1, you can see that this point is dominating most of the solutions here. So it means that we can find solutions which are in this part of the area, but not in this part, because they are dominating. So you find one part of the parietal front. The other case, you can find the solutions which are here, but not this part, because they will be dominated by everyone that is there. If you have this case, you can concentrate on the knees. So it means when you write the optimization algorithms, one thing you could do, instead of running the NSGA algorithm with a normal domination criteria, you change that domination to the cone domination, and then automatically the algorithm is delivering you the solutions which are on the knee points. Example, that was a project we had with Airbus. I'm still having that. And it is about the UAV center, so the big UAVs, and the cost there is a lot. If you make a wrong decision, taking one UAV to do monitoring will cost you 1,000 euros more, 100,000 euros more for one mission. And so they have 7 objectives, of course the cost, then you have estimated time of mission, so next time, risk of mission, number of UAVs, fuel. Some of them are correlated with each other in some cases, but some of them not. And so if you solve that problem, so we said, we do many objective optimization, we found a lot of solutions, we gave it to the Airbus, and they said, this is of no use. Because the guy who is sitting in a ground station, he is a simple guy. He cannot go through 50, and then he has to make a decision in a very short time. So we started working on this cone domination, and instead of finding 50 solutions, we found, well, 3. There are different variations, and we could find, let's say, 3 or 4 solutions. If you look at that, that's the NSGA algorithm. If you have number of objectives 7, we had here 199 solutions that we found. And with this knee point NSGA approach, then we could even reduce the solutions to 2 solutions to give the guy, and then he has to make the decision. The problem here is that you have to find the angles. And for that, we were also developing certain adaptive approaches, because you don't know if you make it small, you still have, well, some more solutions. If you have, you make it larger, you have less, but then you have to know how you do that. And less solutions that you have is also not so good. So you need to have some sort of good number of solutions. So this is for the human users, yes.
Sorry to interrupt. What are the criteria to open that angle? Is it because the data that comes in can have some noise and then it's better to have a certain degree of security there?
No, you want to just concentrate on the knee points.
Yes.
So you want to find them.
I understood that, but why would it be better? Because the others...
Well, if you open the angle 180 degrees, you dominate everyone.
No, I understand that, yeah. I mean, why isn't it enough what you talked about yesterday? Because just to avoid...
Yeah, we want to have, so this here, we concentrate on the knee point. So it means that we find, in this case, we find here, C, B, and E.
Yeah.
So, and it's also very interesting because you can stop the optimization at any time, and then you have some points, and you can claim that they are the knee points at any time, even if they are not the exact optimal solutions. Yeah. Yeah, but this is, for example, one approach you could use. Now let's move on with machines. Can machines make decisions? Like in computer games, you have an agent and it goes into the game. Can it make a decision? So this is not enough that you provide 3 solutions. He has to select one. So here, there is an example that I'm showing to you, what's happening if you do multi-criteria decision making. So you have here an agent who is moving, and I give him 2 functions, 2 objective functions to optimize. One is he has to get close to the point of interest, and the other one is he has to avoid getting close to these obstacles, which I call a danger. This is what is happening in his brain. And one thing you see here, it is a video will be running, what you will see is that this is the Pareto front, or the set of options that he has. And the options are only the directions, so he has 32 directions to select from, and for each direction he says, this is the amount of danger, this is the amount of the closeness to the point of interest, and every time he's evaluating them, he's bringing them in the objective space and selecting the non-nominated front, and then he has to select one. So one thing we do is that you see what is a runtime decision making. So he has to make a decision. At this point, he comes here, makes this decision, comes here, and you see we have fine-tuned it here so well that he is actually doing the work properly. At some point in the video, I change his decision. Now I stop here, change the decision weight vector, and now the decision he's making is he is not going anymore towards the point of interest because I told him you are not going towards the dangerous point. Now I change his weight vector again, and in this case you see that he's changing his decision and is taking 1. So it means one thing we have to do is we give a profile to an agent. We say, this is your profile, you are a risky agent or you are a non-risky agent, and he has that as a weight vector. He goes into the game and he plays it in the way that we want. So the first one that I showed was actually a combination of weight vector, epsilon constraint, a hybrid approach, but in a normal weighted approach would be you can have a whole range of agents, risky ones, non-risky ones, and so on, depending how they start making the decision. But this is predefined by us. The question that we have, here also another example. Here is the roundabout example. This is the autonomous driving car, actually with one of the French companies I'm working on. So here we have waiting time and risk. This is the car he is going to enter the roundabout, and here he identifies the number of solutions that are coming into questions. He finds the non-nominated ones, which are shown here in green color, and then he selects one of them, which is here, for example, as written selected solution number 3. So here he waits for 3 of them to go, and then he enters the third option, and he enters the roundabout. This is a long video. I can provide it later to you if you want with the slides, and but we can wait here that it enters here again, and you can see how it is making the decision, and then I can go on with the talk. But these are all predefined profiles, and the interesting part would be, so now here again he sees that these are the optimal solutions, selects one of them, and he enters the roundabout given that profile. Now, one thing I showed you was this time aspect. So the agent goes into the room and has to make a decision fast. And what we did was no learning. We gave the profile, he has the options, he has to go towards the non-nominated sorting, and that's all. Now the question is, if that agent, so in a very limited time, and usually we have in a computer game, if you have an agent, you have 40 milliseconds to make a decision without, let's say, dying in the game, or the other player acts. And this is like this mouse and the cat. So I'm not now running a perfect optimization algorithm to find the perfect alternative to cone domination or without, but I have just 40 milliseconds to solve a multi-objective problem and select one of them. And I want to learn that. So what can we do? Oh, there is another challenge, the action at time t. So imagine here the mouse. The action that it takes now, it will influence the functionality at the end. So you have to consider that as well. So you have to, when you want to write the learning approach, you have to think about the future, at least the next time steps. The decision now will influence that as well. And you cannot do the pre-planning because you don't know the environment before. So this is very challenging because if you don't know how to go out, you cannot pre-plan, and then everything is not working well. And because you don't know the dynamics, you don't know the obstacles, and you don't know the other agents, it's exactly like in a computer game. You cannot know what the other agent is doing. I don't know who plays here computer games like Unreal Tournament. Yeah, so you know what I'm talking about. So now back from Unreal Tournament to traveling salesman problem. So one thing we do here, so you see here, this is a traveling salesman problem. We call it physical traveling salesman problem. And instead of a salesman, we have a space shuttle, which is going in an environment which is unknown to us. And that environment has normal ground in brown. It has lava stones in yellow. It has bouncing environment, so if you hit that, you will bounce back. And if the salesman cannot go in a zigzag way, he has some momentum. So we give him limited time and 3 objectives: time, fuel, damage. So whenever he goes on a lava, it gets damaged. If he goes long distances, if he makes several runs, it will reduce fuel. And the environment is unknown. You see this is the space shuttle solving the traveling salesman problem. And here you see he's gathering points, which are shown in blue. And there is also some stations here that he can gather some fuel. And you see how his behavior is not normal, like a normal traveling salesman problem. So in order to show you what is wrong, what is different, imagine we take these waypoints here, these the points, the red ones, and if you run a TSP solver, any solver, TSP, I don't know, the existing ones, the traveling salesman solvers, it will give you this behavior, this pre-planned route. If you apply it here to our space shuttle, he will move like this because he has some physical constraint. And the time he needs to go through this will be 1040 units. If you run the algorithm that I will tell you, it will find you the worst web in terms of the TSP solver. This is not very efficient. But if you look how it's moving, because it is considering the environment and the physical constraint, it will solve the problem in 564 time units. So it means pre-planning is not helping you at all. How does it work? We use Monte Carlo tree search. Do you know Monte Carlo tree search? Have you ever heard of AlphaGo? And they won against Zero. They use Monte Carlo tree search. And as our friend Simon Lucas says, Monte Carlo tree search works very well, and no one knows why. This is what I want to show you. Well, Monte Carlo tree search Well, actually, AlphaGo used Monte Carlo tree-stage together with deep learning, but that was another part of it. So one thing, what Monte Carlo does is that you are, let's say, at this state of the game, let's say the mouse, and you identify 3 or 4 more states. At this stage, you identify 3 more states. It's not like dynamic programming that you find a range of actions that you could do. You only find 3 of them, a number of them. And then you go through, well, you know that this is your knowledge that you have from that situation. So you try to select the best ones, the best route. And after some point, you have no knowledge of that. So at that point, you try to estimate, let's say, so I have actually the text here, so you have a tree selection, this is your knowledge of the game at the moment. You try to expand it at some point, so you can do it because you still have time, this is not wasting your time. After that, here, at this point, you do the Monte Carlo, you do the normal Monte Carlo estimation for from the reinforcement learning. Now, who does know reinforcement learning? So reinforcement learning is, how can I explain it? Reinforcement learning is, imagine every day you come from home to university. You have several states, like here. This is your home. Then the next state, you take the car. Maybe here, one of them is you take the car, the bus, or the train, or bicycle. And then, if you take the car, you know the next state is that you get into the car, you drive over the bridge. So for each of the states, you have an estimation. You say, okay, if I get up, take to the car, I need 3 minutes. Well, I need 20 minutes to get ready. 3 minutes. Here, the value here is 3 minutes. Here, if I am going over the bridge, it's taking me another 5 minutes. The other bridge to the university, the other road, it takes me 10 minutes. And at each of these nodes, you write the time that you need. Okay? And then the next morning, you do the same, and you go to the same node and write the time that you took on that day. You write it there. And then you make an average of them. So at each node, you know how often you have been there and how many minutes you use. Of course, if there is a day that you had a traffic, it might change the incremental averaging. But you have the values at these nodes. And this is the idea of reinforcement learning. So you play chess 100 times, or maybe thousands of times, and at each stage you have an estimation what could be the time that you need, the action, what is the value of that action that it leads you to win the game. In the Monte Carlo, one thing you do is that for each state, you think of, okay, at this state, like home, I have knowledge of the value is I need 50 minutes to get to the university. This is the value that you estimate. So it is nothing. So at this stage, you are doing nothing than estimating. So, and that is why we say Monte Carlo tree-stage works, because you have some partial knowledge about the tree. But then at the point that you don't have time anymore to think about what could you do, you cannot build the tree, you estimate. It's randomly. Well, it is not randomly. You basically, like from home to work, you know how many minutes you need, but you cannot guarantee that because it could be an accident or it could be computer games. There is another player, so you don't know how he's doing. Like in computer chess, you don't know if you can win if you do a little action here. Maybe in the other action, the other one is better. So this is the Monte Carlo tree-stage reinforcement learning. In the reinforcement learning, what you do is you have a value for each of the actions that you take. In Monte Carlo tree-stage, so you have I have another picture for that. So you write the value and how many times you have been here as the value of that state. Now, the problem with Monte Carlo, and then here is an equation here, so you have here the tree selection. You are at this state, and then you have the other, the knowledge, the current knowledge, the tree, let's say the tree policy, you can go in, and then from here you expand and from here you estimate. So that's why we write here a Monte Carlo simulation, which is a random guess. And then how you do that, how you select these actions, if you have one objective, which is the case in AlphaGo or other games, if you have one objective, so you always go for the greedy approach, which is maximizing the value of this state, giving a certain action, plus the number of times that you have been here. This is called UCD, and I thought maybe you know the reinforcement learning, that's why I didn't put the slide here. But if you don't know the USB, it is called upper confidence function, and this is here, so you count how many times you have been here and how good that action has been. So in computer games, like board games, in reinforcement learning, you should have a trade-off between how often you have been at that state and if you have not been in that state. So maybe sometimes you want to have exploratory behavior and say, okay, I've been there 10 times, like the mouse moving, and if the mouse, which is going away from the cat, has been in a certain point 10 times, maybe for the 11th time, he's going somewhere else, just exploring. And that end is helping us to explore. Not always go for the greedy approach, but also sometimes we'll going for the exploration. So now, I'm making it even more difficult, so this is for those who don't know reinforcement learning, this is maybe a little bit difficult, but one thing we do is that we do a multi-objective version of that. In reinforcement learning, you have one reward usually. So either it's good in terms of one function or not. You get a reward, you won it or you didn't. But in multi-objective tasks, you have 3 functions that are in conflict with each other. So you cannot stand here and say, oh, I select this because it's giving me the best. No, there is no best in terms of one function. It could be this is giving me the best in terms of one function, but this is giving me the best in terms of the second function. So how can we do that? We actually worked on that. We try to change the equation, and here what we do is we put some simple evaluation of our non-dominated solution. So imagine if you have objective 1 and objective 2, and I have these solutions, these options that I have. Usually in computer games, the Pareto front is not huge, but you have to select one of them. So at each stage here, you have, for each of these directions, you can have a set of Pareto optimal solutions, and then you measure something which is the surface under this Pareto optimal front line. This is the surface which is dominated by them, and you put it here, and you can actually solve multi-objective problems. Now let me show you how it is working. So this is a video, and you see what is in the brain of the agent, what the agent is deciding. The colors show the relevant, and every line here is showing one of the branches that we have in the Monte Carlo tree search, and the colors show how good that certain behavior is. So the red is the good one, the violet ones, they are not so good. You don't see the profile of the environment here, the map is not shown. But one thing you see here is that the agent, this one, if you would have used a traveling salesman solver, you would definitely pick this red point because it is on the way. But this solver says, no, this was not a good option to get here because it will not fulfill your physical constraint. So it is getting here, and here. And again, if I make it faster maybe, you will see that the agent is making different decisions than a TSP solver. And one thing you also see here, the length of the tree is small. So all this decision is made based on in 40 milliseconds. If I make it faster, you'll see here that we didn't hit this one from here. It went up and down because it could estimate here if he will not hit that point if you go with the normal TSP solver. So then, one thing you have to do on the top of this is to make decisions anyway, because then you have each route, you have to, the root node itself has to be selected based on the preferences. And here what you're seeing as a result, you can see if we only go preference objective 1, so at each time step I say I only optimize the first function, or the second one, or the third one, or an adaptive approach, you see that this agent for the adaptive approach in different maps is able, for example, if you look at the time, fuel, and damage, in all of them, it is getting better than the others. So it means you do this Monte Carlo research, multi-objective version, and then every time you make a decision, you look at your 3 functions and say, okay, I don't have much fuel, so I will go try to optimize the fuel, and then let's see what is next time. And next time you say, oh, I don't have much time, I have fuel, I try to concentrate on this one. And next time you see which function, so you put all the 3 functions, and then you change your preference, like you say, okay, 3, I'm minimizing the damage, I'm minimizing the fuel, number 2, I'm minimizing the damage, I'm minimizing the time, and in this way, in an adaptive way, you can actually make good decisions, and then you can actually end the episode of the game to come to a good solution. I don't put the videos for that, but then I will provide you the videos for the multi-objective. When you compare that with the random selection or other preference-based approaches, you will see that they are actually working quite well. But now let's go on collectives. And the first thing that you can implement if you have a swarm or a collective, you want to see if you change something in that collective behavior, if you give the agents the capability of making decisions on their own and not to follow the swarm. So how can we do that? Let's imagine we have a collective search. We have the robots flying or moving, and we tell them collectively find the 2 points of interest. So now we don't have one agent, we have many of them, we don't know where the point of interests are. They have to collectively find them. It's like solving an optimization problem. For this approach that you can see here, we can use, for example, we say we have a search space, usually it is n-dimensional, here you see 2 dimensions, and then we say, okay, you have to gather k points of interest, so these 2 red points should be gathered, and so it is the minimum, let's say, of this function that we are looking for. You use swarm intelligence approach, so you have the leader selection like we had yesterday, and each solution is selecting the best in its neighborhood and is moving towards that. Like birds flying in the sky, you always follow the best in your neighborhood. So now, one thing I say is that don't follow the best in your neighborhood. Now do whatever you want. So I change that. I say, okay, for an individual, I say you look at, we call it energy-aware collective search, and say, okay, whenever you look at your neighbors, so you are now in this collective search scenario. Of course, you want to collectively search with the others, but you have also a limited energy. Like flying robots, they have very limited energy. So we tell them, so now it is in the brain of each of the agents. It looks at its neighbors and evaluates them. It says, if I follow this agent, is good for saving energy, but is not giving me much profit in terms of solving the problem. If I select this one as the leader, is giving a lot of profit, but I need to spend a lot of energy to go there. And these are actually not good leaders because they're worse than these. And then if you could select this one in the middle, it would be a leader which is middle in the profit and middle in terms of the cost. So you have the neighbors, so instead of selecting the best, you evaluate your neighbors and say, okay, now I select this one or the other one to follow. So we can have that agent, we can give him, let's say, a preference, risk again, Ri, and it could select, for example, some of them could select only this one, some of them could select only this one, but with a predefined vector. Or you can also look at your energy level and say, okay, I'm flying, and I don't have enough energy to follow that guy, who is the best, but I will follow the other one, and it's helping me to save some energy and still be active in the collective. So you see here the collective search. This is the default search. These are the decision makers. So now these decision makers, they are not following the entire group. Everyone is thinking if I should move or not move. And you see they are very slow because at some point they don't move because they see that there is no benefit in moving and doing something for the collective. And these are the default, they are moving permanently, and the minimum is actually here somewhere in the middle, and they are not even able to find it as fast as decision makers. In terms of the function values, I don't know why this is here. So in terms of average values, you see that the red ones, they are better at the end, but in terms of energy consumption, which is this curve, you see that the energy consumption of the blue ones is less. If you look at the lower the value, the better it is, and the red ones, they have a lot of energy consumption. Another example here, the decision makers, they are very slow. They have also very weird movement. Here, like a worm. They don't move much, but if they move towards the best in terms of energy and also in terms of and the minimum is somewhere here in the middle. They will be slower, they're much slower. The blue line is much slower than the red line for the default, but the energy should be always very small. You see that the blue ones, the decision makers, they have a very low energy consumption comparing to the red ones that are still moving to find the optimal point. I later applied this to the robotic application, show you some videos there. But let's go on. So it means that if you have this decision making, you can give it to your robots and they can also make interesting decisions. For example, you can say, move to the point of interest, but do not fly against the flow because it will reduce your energy, and fly into the flow. And at the same time, you have to minimize the search. And you can see here the decision making is a little bit interesting, but I actually removed the details for that because it concerns also a little bit uncertainty. So you don't have the information about the environment. What you see here is the agent has to make a decision. These are the directions that he has to select from. For each direction, he has to estimate, if I go there, how much wind is against me, or how much energy I need to go there. And the only information he has is based on the blue areas here. So he has a lot of uncertainty in making the decision. And if you implement that, you will see the decision makers, so the optimal point that they have to go there is here, and you see you have a lot of flow against the movement. And the blue one, the blue points, they don't see the environment actually. They're just for the ground truth. You can just see them how they might move if there wouldn't be an environment. And the decision makers, you see, they sometimes go with the flow and they follow to these points, which are not basically optimal, but some of them end up being at that point. You can see how the intelligent behavior could be. If you put them in other environments like this, you see how they behave. This is a very artificial environment, but you can see here that they are moving along the vector fields to save energy. So they are very intelligent. Now, we put this behavior, the decision-making behavior, in a random environment like this, which is also a very artificial environment, and you see that the purple ones, they are not efficient. So that means if you give them a capability to make decisions, make them a little bit more intelligent, it is not going to work here for random environments. It only works if you have structured environment. Another thing that you could do using, for example, an approach, which we probably don't know about, but is called genetic programming. In the genetic programming, we can use the ideas from evolutionary algorithms to learn the movement equations. We can use that. For example, we say, okay, this is the point that they have to go, but we don't know how to go there. Now, just in the last slide, I was telling you, okay, you make a decision and you don't go against the flow, you go with the flow. And now what we do is that you can change you can learn how to move in such environments. This is done, for example, with geometric semantic generative programming. And what you can see here, the agents, they try to learn to move against the flow. And I don't know who is a sailor in this room. If there is a sailor, the sailors know if you want to go against the flow, you have to go zigzag. And what they learned here, also these ones, they all go zigzag, and these as well. But these ones, they just go with the flow because their flow is helping them to be faster. So with these approaches, like generative programming, you can even try to learn how to cope with such environments but this is out of the scope of this work. So now I still have a lot of slides to go. So now, this individual decision making and the collective decision making. So from one side, we say we want to have a swarm behavior. Everyone should follow the best because it is the best. From the other side, we say no, you can now make decisions if you want to follow or not. So we have something which called, in German we call it Individualität and Kollektivität, and it's individuality and collectivity. And the question is, what percentage is important to have a good collective system? How many of them are allowed to be deciding, and how many of them are not allowed to be deciding? And this is some, let's say, philosophical questions, and also from the nature, you see always a group of animals. Some of them, they go the way, and some of them are followers. But what percentage is required to solve the task? And the other question is if we can influence the decision-making of the entire system. So, in nature, people have done that, and this is for you, Jim. I put this slide. Fish. There's a scientist called Ian Cousin. He worked a lot on the collectives in nature. So he trained two groups of fish. These are the zebra fish, but don't ask me their exact genes. They're smaller probably. Yeah, so you can train them. And before that, actually, I wasn't aware that you can train fish. I was thinking you can train dogs and cats. But you can apparently train a fish. And you train them, for example, the first group is trained to go to the colorful area. So if you put them in this experiment and let them go, they always go to the colorful area. They are trained for that. And then you have another group which are designed to go to the stripe. So whenever there is a stripe, like here, they go towards the stripe. They don't go towards the colorful area. Now in this experiment, what they did, they put another arm, which is called consensus arm, and this arm has the color and the stripe. Now they put the agents, the blue ones, they go towards the color. The striped ones, they go again to the stripe. Now they put half of them, so put both of them together here, and they realize that half of them end up going into the consensus. How? They analyzed that, and we replicated actually the work, and we said, okay, we believe that they are having some individual and collective behavior. We want to know the percentage, and we do this kind of multicriteria decision making. We say, okay, this is the distance to the target, and this is the cohesion. Cohesion means how much you want to be with the swarm. So if you follow the swarm or not. So if you're the lonely one from the train group A and everyone else around you is B, you get convinced and go with them because you don't want to be alone. And if you are group A or you are in the front, you just follow your own because you don't have anyone that you can follow. And this is the decision making. So either you go towards the personal best or you decide to go with the group. And if you do the experiments based on the multicriteria decision making that we gave that, we could replicate the work of Ian Cousin for the nature. We cannot claim that this is the same, but this is interesting to see. If you give them these two conflicts, you can actually replicate that. And this is here, how many percentage they ended up in target A, how many percentage they ended up in target B, and how many ended up in consensus. And you can see that half of them, they ended up in the consensus arm. the same, this is the number of agents in several runs. You can see that this actually can happen. Now the question is, how can you influence actually the agents? How can you influence the collectives? Can you influence them, and how? And this is a very interesting research. If we can, and then goes actually, there are colleagues from Switzerland, sociologists, they are thinking about how you can influence people over Facebook, how can you do these things. This goes to that direction. I am interested more in another application. Let's imagine we have an environment. The application for that is actually very nice, but let's see what the problem is. Two-dimensional environment, two colors, white and black. Now you have a bunch of agents, and you want to ask them which color is the majority in this environment. And they can only observe the value that they are on it. So here, the collective this is a collective perception. You don't know which color is the majority, and at the end, they have to find out which one is white or black. So what they can do is, I can run the video. What they can do is, they are moving in this environment, and they gather the information. For example, this one says, oh, I am here in the black, and black, and black. And whenever they meet the others, they exchange the information and say, okay, I have seen black in the last 10 time steps. This says, no, I have seen white in the last 10 time steps. And if you exchange the information with all your neighbors, at the end is a majority voting. They say, okay, we come up with a decision that the majority in this room is, for example, black or white. So this is a very interesting research topic. If you are interested to work on, I can recommend. It's very interesting to implement that, and you can start working on collective decision making easily using these sort of examples. And now, one thing we do is that we change this environment to this environment. This is a little bit difficult because the percentage is very tight. I mean, 48 and 52% is very tight. So the swarm is not able to solve this problem. Sometimes they solve it, sometimes they don't. You can see here the black is those who think that this is the black, they are red ones, and you see most of them, they are convinced that the black is the majority here, but actually white is the majority. And unfortunately, they will not find it. And this is because it's very, very tight. The application of this is up to here. The application is very interesting. It actually was a project we had with the marine in Ireland. And there are algal blooms there, and the fishermen, when they go fishing, they have to see if there is algal bloom there or not, because they're toxic. And they have to measure the amount of toxic material in the water. So one thing they do is that they go on a boat with an Irish fisherman, has a big sensor, puts in the water, and measures, yeah, toxic or not. The goal was that we make a group of swimming robots, we send them, and they have to measure, and then at the end they have to say how much is it toxic or not. Algal blooms there are okay on that day or not. And that would be the application for that. Now, this doesn't work all the time. And the question is, how can we change that? And then we were working a lot on this, and we realized if you change the environment, it doesn't work on this algal bloom thing. But in theory, one thing you could do is that if you use the isomorphic transformation means that you keep the proportion of black and white, but you just change their order. And if you do that, this is the same percentage, but the different setting, you will see it was very fast. They could find it. So it means you can actually, what Facebook is doing all the time, you can actually influence the collective decision making by changing the environment. You cannot control every single agent, but by changing the environment, you are actually fully capable of helping them to solve certain problems. So now, see, I was doing all these things. Now, one thing I want to show to solve a multi-objective task. Until now, I didn't have multi-objective task. Now I give it a multi-objective task to say, okay, now they have to really learn to solve this. And for that, we give tasks with conflict. We use evolutionary algorithms. And this is the environment. So you see these are agents. And they have to go from one room to the other room. And they have to do the gate passing and avoid collisions. And if we have that, let's say this example here, if we give them the behavior to go from one room to the other and avoid collisions, I think I have it here, gate passing and avoid collision, exactly in the middle here, they have problem. So one thing we don't tell them how to do that. We say, this is the fitness function that you have to be measured every time you are moving. We measure, this is what I write here, fitness of a behavior. Every time you move, I'm giving you a task and I am measuring your behavior based on that. In this case, for example, every time, if there is no conflict, the fitness function is very simple. It's you measure how often you have collisions. Here you have complicated tasks. This actually can also be interesting for those who want to have some theoretical works. You can actually do a lot with the fitness behavior. For example, you can have explicit behaviors or implicit behavior, but at this time I would, let's say, skip that and go to the idea how we implement. The idea of implementation such a behavior comes from Breitenberg, who was an Italian scientist, and he was working on the psychology of machines. And he said, this is a robot, this is a motor, this is a sensor, and so it moves if the sensor value, for example, if there's large values for the sensor, the motor is moving faster. So here, if you have two motors, like a robot, like moving with two wheels, you have these sensors, you can actually program it in a good way. For example, if you have, this is actually what I would do. If you have, for example, I have actually an example here. So let's say we have here temperature, we have sensor values here, sensors, and if this sensor is connected to this wheel, what does that mean? So you have more temperature, the motor is turning faster, so you are turning. And if you have this scenario, this sensor is connected to this wheel, this is moving faster, this is moving slower, so it means that you're turning in the other direction. In this way, you can have a behavior of your robots. And he called it in his book, for example, fear or aggression. So it means this is an aggressive behavior and this is a fearful behavior because it's going away. Now, in our case, we have something like this, which is very difficult to program, right? So you have a lot of robots, your agents moving in a certain environment, a lot of sensors, and the two wheels. Now, how can we learn that they go from one room to the other, avoid collisions, and perform the task? It will be difficult. So you can use the binary concept, but you have to see how to program it. And this is the application, so you have to write a controller which connects the sensory to the motor values. These are the robots, let's say, and these are the sensors around them, and we want to program the behavior that they, for example, turn right or turn left. Many of you, as I saw yesterday, you work on neural networks. You say, oh, I put a neural network there, and I can solve this problem. You have the motor space, sensor space. The controller is telling you which combination of the sensors would be proper for the wheels to change to avoid collisions or turn left and right. And this is the area that what for many of you would be interesting. This is the area of evolutionary robotics, that they try to learn and adapt to the dynamics in the environment. And there are two ways of modeling that. The neural network one would be like you have the sensors, output, input, and you can program that. The only problem is it takes long to train because you need to gather the data. Now what I want to show you is that how you can use finite state machines to learn a conflicting task. So we use these finite state machine-based controllers for onboard learning. Onboard learning means the robots go in the room, we give them the task. The task is collision avoidance, gate passing, and movement, and that's all. They have to learn it on their own in a given time. And the final state machine, I think I don't need to go through that. You have several states. For example, this could model this behavior. If you had only one sensor, it would be move, and then there is a transition as long as this sensor is giving you some value, you turn right, and so on. And we want to learn that. So we are getting close to the hardware. And these are the wheels. The turn right means the wheel, for example, right, the velocity is smaller than the left, turn right should be left, and so on, so that will be the behavior of the agent. So for you to see how it would work, these are the robots, and they actually have to learn to do these tasks. Okay, so what we do is we use evolution robotics. We start with a group of robots. Everyone has an empty controller. And over time, every time they meet each other, they compare their fitness values. He says, oh, I have this amount of collisions, I had this amount of gate passing, and the other says, no, I had this amount of collisions, I had this amount of gate passing, and the one who was better will give its controller to the other. So if you do that, you can also have mutation, because you need to have new controllers, so they add new states, new transitions, and then they can solve the problem after a certain time. So a designer, a human designer, this was my PhD student, he designed this behavior. He said, okay, you go here and do this butterfly movement. What the robots learned was something else. They said, no, you go towards the wall and follow the wall. If you follow the wall, there is no collision, because everyone is on a row and follows the wall. And you also go through the gate. And that's a very clever behavior that the human designer actually, for this very simple behavior, couldn't actually deliver us. This is the state, the machine, the controller that we evolved. It's not much big because you can only reach the black part of it. The gray parts are not reachable. But I just wanted to show you, sometimes we produce things that are not really doing things. And this is the behavior. So, and the number here shows the number of generations. So it takes a long time that they evolve the behavior. And one thing you also see here is that the agents are doing the wall following. Most of them are doing this behavior. There are two here and one here that they are lost. And this is the behavior, the swarm behavior. So if you look at ants outside, not everyone is doing the perfect job. So as long as the majority is doing the task, it's actually a good behavior. We replicated that actually in the year 2017. Actually, that's the work on consciousness that I told you yesterday with Tononi. And I call this, we replicated this work actually with some other modeling. It's not anymore financial machine, but hidden Markov models. And I call this Chinese military. It comes because it moves like that. But if you wanted to analyze another behavior, and you can see here, we cannot explain it why, but we know that we don't have a mistake in our code. And we are trying to actually publish in this. Two of them stop work here, and one of them stops here. The modeling is a little bit more complicated than the other one, so we use hidden Markov models, and the crossover and mutation that we apply, it is different than the one I explained you. But you can see that they, more or less, they can replicate what we had. The wall following is the solution to this problem. And they stop here to help the others to do the task in a very efficient way. Good. So now I come to 3 more points. The first point is you can actually use this multi-objective optimization for analyzing the behavior. And this is a project that I have with the Leibniz Institute for Neurosciences. And I don't know, who plays Dart here? But you know the game Dart, right? Have you seen Dart? Playing Dart? So we work with Leibniz Institute Neurosciences, and we use this multi-objective thing for analysis. We are not optimizing, we are not making decisions. We want to understand what is happening in the human brain. So this guy, there are many of them. Actually, I didn't know that people would voluntarily do that because you have to get this helmet and a backpack is the device, and you have to play 500 times a dart. It's a lot. Actually, 500 times for me is a lot. And they are now professionals, and we want to see two things. We want to analyze two conflicts in the human brain: precision or accuracy. So here, for example, if you play like something like this, of course you want to hit the middle, the bull's eye. So this is a good accuracy because the average brings you in the middle. Let's say you play 10 times or 500 times, you can see where is the cloud. If you have here play like this, you have a very good precision, but very bad accuracy. And this one is neither accuracy nor precision. Most of the people start here, if you're not a professional. And so we have these two criteria, and people like us, we unintentionally either optimize accuracy or precision. So no one is the best. So we had a Pareto front of solutions. So we gathered the data. So this is 50 EEG channels, EMG signals. So we have the so-called shimmer sensor. So there's a sensor, acceleration sensor, that you could measure how fast they are moving their fingers. And we measured precision and accuracy for both. 500 times, we divided into different groups. The first group, the beginning, and then the middle, and the last. So one thing you can see here, this is the precision and accuracy of all the people who were the 17 people. No, these are not 17 people. There have been more. I will show you the other slide. But these are how human would play. So you can see here no one, and you please note that we are minimizing accuracy and precision, which is actually we want to maximize that, but in here the graphs, they are all towards the minimum. So the less, the better the value is. You can see that no one is the best in terms of precision and accuracy, because we don't have one point that is dominating them. For example, if you look at the front 0, which is the best front, you can see that someone was very good in precision and accuracy, but this one was better in terms of accuracy, but not good in terms of precision. And the other one was, for example, the best in terms of accuracy, but not as good as the other one, the blue ones, in terms of precision. So now you can analyze these non-dominated solutions, and you can have different front lines, and you can analyze what was in the brain of this guy who was playing here, what was happening there compared to the guy who was here. You can also say, okay, I categorize, I cluster them in terms of accuracies and precisions, and this is all what we did. And one thing you can do is that what is happening in the brain when you are playing 500 times? Are you getting better? And how you get better? And this is actually something very interesting. For example, we have for one person, he started here, and you see he was very bad in the beginning, and then he improved over time. Well, he is not the best, but we are not talking about the professionals. And then we analyze what is happening in his brain and which parts of his brain, so the X variables that we have, are influencing to get this. And so on. So this is actually a very, very nice project where we, for the first time, we were using this multi-objective, and it's not anymore optimization, but it's analysis, to analyze the data that we have in terms of several criteria. Good. So now I show you some decision making on real hardware. I work also on robotic applications, and all these approaches that I tell you, we apply them also in robotic systems. One of them, for example, is this robot, is flying and making a decision. It's a fully autonomous robot, and the decision that it's making is actually a simple behavior, is avoiding obstacles. So every time it's moving, he has to decide which direction he has to go, and it's actually doing quite well. You see that it is really avoiding everyone in the arena, that also the one who's taking the camera, the picture. And the other one, what thing you could see, and I want to show you what is in the brain of what is happening, how the agent is thinking. This is the important part of that. So now, one thing we'd say is collision avoidance, risk, but gather point. So this is the agent, the black point, and the green point, I'm sorry that it's very small, I hope that you can see it, is the direction that he's thinking to go. So we see what is happening in his brain and how he is changing his decision over time. So you see here, we tell him, okay, you have to gather this point, but here I put the wall. So collision is not good. So he comes here and you see he's thinking, and at some point here he will change his opinion. He wants to come here, but he changed now and said, no, it is too risky for him. It's not coming through here. So he goes here and hopes that he can get here into this area. And again here you can see he wants to come here, but he changes his opinion, and he's going back and forth, but he's predefined. We gave him the preferences to be very conservative. Now in the other video, we give him the preference to be very risky. And you can see for a flying robot, it's very dangerous to go here. And you can see here, it just doesn't care and comes here. Now, we put this together, we make the decision making at runtime, and he has to make the decision on his own with full autonomy that we give him 2 points. This point is closer, the same situation. And you see how it is working. Of course, he has to go first here because the solver tells him, look, this is closer to you, you should go here. And you see how he's thinking? In the beginning of a mission, he doesn't want to have a lot of risk. So he goes here and he sees, oh, it's too tight. It doesn't go inside, changes his opinion. He says, okay, like, in an Unreal tournament, you say, okay, I forget the point. I don't want to gather that point. It goes there to gather the other point. And it will. And at a certain time, he says, oh, I still have some time. It is very tight timing, but I see if I can go back and change my preference. And this is what happened. He gathered the point, he changed the view of the simulation, and you can see here, at this stage, he will make the decision, he will take that decision, and he will come here and will gather this point. So you can have agents that they change their decision-making profile at runtime. And yeah, so it's very tight actually. We couldn't run it in a real hardware because of the risk that we use micro robots. But one thing we could do here, for example, this is a little sparrow. I don't know if you know the Star Wars movie, the BB-8. This is the BB-8 one. Same functionality, is rolling. And they have a lot of mistakes because if they're rolling, you tell them roll 50 centimeters forward, it goes 20 centimeters left. So a lot of mistakes in the system. And you tell him, avoid this object, but he doesn't know where the object is. And you see here, this is the way the hardware works. It's very simple. And here, for example, I like to put them in a conflicting area, so you have to go between these two, but do not touch them. So he found this object, and now he has to go, he has to go exactly in the middle. Just did the work. So, yeah, so you can you can implement all these ideas that we have also in hardware and see how they are working. So now I come to the last point of my talk, is I talked about decision making. I basically gave you a lot of things in decision making, lots of individual decision making, human agents and so on. But if you have agents who make decisions, then you enter the area of ethics. And the philosophers come to you and say, oh, if you write a code and put it on an autonomous driving car, the roundabout one, if there's an accident, who will be responsible for that? You as the programmer, the company, or who? And there is for us computer scientists, we have the Hello World thing. The people from the law department, they have the first Hello World assignment, which is only a thought experiment. And this is called the trolley dilemma or problem. The trolley problem says, who knows trolley problem? Oh, there are some of you. So the real trolley problem problem will come, but the idea is, imagine you are driving and it is a road and no one is allowed to cross the road, let's say. And there are 5 children who are there and are illegally go over the road. And you are the driver, and now this is the situation. 4 of them are in the middle of the road, which they were not allowed to be there and cross the road. And one of them, which is a good boy, a very good boy, is standing at the sidewalk, at the side, and is not on the road. And now this is the dilemma. You have only 2 options. Either kill 4 of them, or kill the one which is there, which is actually innocent. What would you do? So this is the hello world, example that they have to debate on that and so on. And imagine if you write code, decision-making code, weighted sum approach, epsilon constant, whatever. Who is responsible? How would you do that? How can you incorporate that? And the real trolley problem is actually a different example. It comes, I just put the picture from here, so you are testing, you are here responsible for this test, and there are 5 people here, 1 person here, these are the workers, and so this person is the one that was supposed to work there, and these are the people that were not supposed to be there, and you were told that you will, you will support this person. You will not let this train to go there because he is working there. And now you see, oh, there are 5 people here, and now you have to make a decision if this will kill this 5 or this will kill this one. So this is the trolley, the real trolley problem. And this is, of course, something that you have to be aware of. And I'm not a philosopher to do that, but there is one nice video I wanted to show you. I had to show you, this is a joke. But I thought at the end of the talk would be something refreshing for you. So this video, I don't know those who know ethics, maybe they know that. There is a child. Do you know that? So this is the answer of a 2-year-old child to this trolley problem. So the father asks him, you have 5 here, 1 here, what would you do? Okay. Well, decision making is a challenge. Now I come to the conclusion. Decision making is a challenge for both humans and machines, for all of us, and whenever we make a decision. At runtime, it is a challenge. And we can actually optimize the functionality by giving them the ability to make decisions, especially in hardware, in robotics. We can give them flexibility to change the planning. And I wanted to show you that you can change actually the decision making using the dynamics, changing the environment, and then in this way you can influence the swarm, the collective. Okay, so I'm at the end. Thank you for your attention. I'm happy to answer your questions.
Okay. Salas, thank you very much for your nice talk. We are running 10 minutes late, and that's because we wanted that some people did arrive in the morning, so we had some people watching. You usually don't do that except if it's the last day, because otherwise people can think that they can come even later. So anyway, okay. So we are not running late actually because we modified the schedule. Do we have any questions? Okay.
Yes. What was the information of the robots in the case of obstacle avoidance about the environment?
Well, the environment is, if you have a robot, the robot can have only the sensory information. And you say, okay, you are with others, you have to avoid collisions. So every time, it's sort of a reinforcement learning. You say, okay, every time that you have a collision, you have a bad fitness reward. And then I tell them, okay, you have to go from one room to the other. And this is a conflict, because then, you know, if you go through the gate, you have most of the collisions. And we didn't tell them how to do that. We said, you learn together how to do that. We didn't consider the environment. But if you consider the environment and that model, you actually do not need to tell them what to do. So this is sort of implicit fitness function. So basically you let them there and say move, and every time you meet, you exchange the environment. But then if you don't tell them what is good or what is bad, every time they meet, they change the information, the controller that they have evolved, 50-50, because there is no one better or the other one. But imagine there are many of them. So I am moving and I have a very good controller, and then I bump to you, and then 50-50 I exchange my information probability. If you are worse than me and you give it, so I'm gone. But if I have the chance to give it to you with a 50% probability, now there are two of us moving in the environment. And then if you, then we have again the same 50-50 chance to see others and give our controllers away. And if you can model, if you model that using Markov chains, you can actually see what is the success rate. And then at the end you see that you don't actually need a fitness function. You can actually put them in the environment, and the environment implicitly gives you the fitness function, because if you are in an isolated part of the environment, you will not meet anyone else. So you don't, your fitness is very bad because you are not meeting anyone else, you are not improving by communication. And those who are communicating a lot, they of course have the chance to lose their information because everything is probabilistic based. But if they give it away, then there are many of them who are doing that, and then that will increase your the fitness of the functionality of the swarm. This is a very nice work, actually.
Another question?
Somebody has one of the audience has a question. Maybe she will. Is your question?
You are part of the audience now.
Okay. I'm not an expert on this by any chance, but several years ago I had a grant in an area called human geography. It's about how people make decisions based on ethnicity, income, tribal behavior, whatever. And we were looking at you have Hicks law. You were talking about Hicks rule or whatever, that you limit the number of alternatives because otherwise you get confused. We were looking at something called bounded rationality, which was a psychological thing that came up in the 1950s. A guy by the name of Simon did it. And in that case, you don't limit the number of alternatives, but you limit the number of criteria. So basically, the idea was that if a human's going to make a decision, they're not going to look at all possible criteria that affect the problem, but only the ones that seem to be present, right? The ones that are expressed most right now. I don't know if that...
It's a very good point. It's an extremely good point. The thing is, we were thinking to do that with the Airbus application, because we said maybe some of them are correlated. Cost and the number of UAVs, they are definitely correlated. But they said no, because the cost is also something else. It's, of course, one UAV is 100,000 euros if you take for the mission, but it also depends how long is the mission. So that is also the other things, and the satellites, and also the forbidden areas, and so on. So, I was thinking to do that as well. I said, okay, he's a simple decision maker because he is not interested. So why should we give him 7 criteria? We give him like 2, and then we solve it for him. And they said no, but I think this is actually a very good idea. But it's very sad, actually, because as a decision maker, you really want to have all the criteria. And if they do it, psychologically, you can do it on human behavior. Yeah, but you can also see in the election, for example, if there are more, like what happened in England, if you had only Johnson or Corbyn, that would be easier than if you have also 2 more. you know, and then you can see the outcome. If you have more, then basically the one that is not probably desired would go out, would win. And you know, there is a very nice work from Frank Schweitzer at ETH in Zurich. He works on this, and he analyzed the election in France. Then Jacques Chirac won the election, and he was minority. He was minority of 25%, and he still won the election. So all the people working on decision making and collectives and so on, and swarms and so on, they really liked that application. And he wrote a paper, sometimes minority can win. And he analyzes how the decision making is influenced. And I think he has some sort of work in that area that it reduces the number of criteria in this direction. It's a very good point. I will think about that, definitely.
Okay, any more questions? We have time for, I think, one. Okay, please.
Yeah, I have a question. When you talk about the goals, you can make a preference to the agents to solve some kind of criteria?
Yeah, you can give them a weight and say, okay, if you have a bunch of robots,
yes.
you can say, okay, this is conservative, this is, yeah.
For example, preference based on adaptive.
Yeah. So no, what the other thing we did was, what we are doing, we have a bunch of robots or agents, and say, okay, this is the conservative, this is the middle one, this is the risky one, and so on. And we put them together, and we say, okay, now solve the problem. And then the interesting question there is what percentage of what behavior you need that at the end they end up doing the task. I mean, if you have the risky agent, he might die fast because he will hit the wall and so on. And if you have a conservative one, he's not moving basically because everything is too dangerous for him. So, and then you have to see how many you need to have from the conservative. I mean, the one that is going back and forth is not helping us because he's taking all the battery for 5 minutes, he can fly, and he's going from one direction to the other to make a decision. And the other one, the risky one, is also not helping. So we are working on these number of percentages, how many of what sort you need to do that, or do it and adaptive. Adaptive is the simplest one, which we already published, but the other one, which proportion, it's a good question, and we don't have any answer. We know that if you have too many conservatives, it will never end up a mission. So the swarm will never do that. And if you have more risky agents, that will also never end. And this is coming to the game theoretical aspects. I don't know if you know the game theory. So it's like you are a fisherman and you have fish. If you take all the fish from the lake, then you have tomorrow, you don't have all the, a week later you will have no fish to eat. So you want to keep certain behaviors, some bad behaviors, some good behaviors, so you want to have a balance, so-called evolutionary stable strategy behavior and so on. It's getting very theoretical, and still we don't have an answer for that. This is a good question.
Yes, and for example, to choose, if you put adaptive agents with predefined risky agents, for example, you can see an improvement, for example. If you put a predefined, for example, in a mixture, but you compare with the adaptive behavior, you can always see an improvement with the adaptive. That is more
we can. One thing you could also do that we have not done yet, but you could do that if you're interested, is that you learn the weight vector together. So everyone starts conservative, and then you try to evolve the weight vector, which is a small vector. But then you will learn it how to do it, or to learn it at the end, and come up with the best decision-making preference. But still, the weight vector, as I showed you yesterday, is not a good thing. But still, in the robotic area and computer games, we are still in the weight area. So you can also do some sort of epsilon constraint or hybrid approaches, which I didn't talk about. But you can see how far we are from the real optimization when you do the optimization in the decision-making game. But that would be nice to try it.
Okay, one more question.
It's not a question. I wanted to thank you because it was very, very nice, very clear, and the examples, and how interesting it is to to try to modulate in some way how human beings are taking decisions, and I wanted to underline the importance of that, because when you have multi-objectives, you can start finding, for example, applications in environmental, in how you say that? You can pick up the ecology, the economy, all these variables that are so critical nowadays, and making better decisions, looking for the climate, the forest, and everything that is being so wrong. So thank you very much.
My pleasure. Thank you.
Okay, now I think we should go for the coffee break. We will want to say again, Sana.